So the zeroth law of thermodynamics helps us to define the temperature or gives us the concept of temperature. So we know this according to the zeroth law of thermodynamics that if two systems are separately in thermal equilibrium with the third system, then they will also be in thermal equilibrium with one another. So thermal equilibrium means there will be no heat transfer or no heat flow between these systems constant. Okay. So now how can we be sure that there is no heat transfer or heat flow between the systems? Because we cannot see that heat is flowing from one system from another system. We also cannot measure what amount of heat is flowing from one system to another system. So how can we be sure that there is now no net heat flow between the systems? Okay, so there must be some property or quantity of the systems looking at which we can be sure that okay, when this value of this property is such and such, then it means that now the systems are in thermal equilibrium. Okay, and the net transfer of heat is now 0. So that property is basically the temperature. So in this way, the zeroth law helps us to give us the concept of temperature. So temperature can be defined as the thing, okay, or concept or idea, okay, which is same between the two objects or systems when they are in thermal equilibrium. Okay, so when two systems or objects are in thermal equilibrium, we can say that at this point the temperature property of the systems or the object are same for both of them. Now suppose in some universe, okay, for example, which is not ours, okay, so as we have seen that suppose the iron and wood are in thermal equilibrium, okay, there is no heat transfer between them. Then iron and water, so this was the iron and water in thermal equilibrium, no heat transfer. Now suppose in our universe where the zeroth law is suppose true, then when the wood and water are put in thermal contact, then they should also be in thermal equilibrium. Now suppose in some universe when the wood and water are put in thermal contact, they will not be in thermal equilibrium and there will be heat transfer between them. Okay, but thankfully in our universe such case does not happen. That is the zeroth law of thermodynamics holds true. Okay, so when the iron and wood are in thermal contact, thermal equilibrium, iron and water are also in thermal equilibrium, then wood and water will also have to be in thermal equilibrium and there will be no heat transfer. Okay, so this allows us to, so this allows us to define a universal temperature scale. So what is the meaning of this universal temperature scale? For suppose all this iron, wood and water are in thermal equilibrium. Okay, so in thermal equilibrium, suppose the first object, which was the iron, its temperature is 20 degrees centigrade, and the wood, its temperature is also 20 degrees centigrade, and the water, its temperature is also in 20 degree centigrade. Okay, so without putting them in thermal contact, you can clearly say that, okay, because as all of them are 20 degrees centigrade, without putting in a thermal contact, you can say that they will be in thermal equilibrium as per the zeroth law of thermodynamics. Now suppose if such was the case, okay, if this was the case that this 1 and 2, if you put 1 and 2 in thermal in contact, there will be, suppose you see that there is no heat transfer. Okay, their temperature is same. Okay, but when you put iron and wood, you see that there is no heat transfer. Okay, then you put this first and the third, that is iron and the water in thermal contact, then you see that there is no heat transfer. But when you put this wood and water, okay, so second and third in thermal contact, you observe heat transfer. Then what will happen? Then so the problem with this is that so the for the iron and the wood pair, that is 1 and 2, the temperature scale will be, as there is no heat transfer, so we can say that both are in temperature according to this temperature scale, both are at temperature 20 degrees centigrade. Now when the first and the third are put in thermal contact and you observe no heat transfer, then they are also, according to that temperature scale, the iron and wood are also in 20 degrees centigrade. But suppose according to the same temperature scale, the okay, so now when the wood and water in put in thermal contact, you observe some heat transfer. Then you cannot say that according to that temperature scale, but according to that temperature scale, they are in same temperature. But when there is thermal heat transfer, you cannot say that they are in same temperature. There has to be some temperature difference between them, between wood and iron. If there is heat transfer, net heat transfer between them, but the temperature scale you are using, they are in same temperature. But if there is heat transfer, you cannot say that they cannot say that they are in same temperature. So now you have to define a new temperature scale. Okay, so now you have to define a new temperature scale for this wood and water pair. That is, for different pair of objects or materials, you have to define new temperature scale. So it will not allow us to use an universal temperature scale which will be applicable for all objects or materials. But thankfully, this is not the case, right? This is not the case, because if you put wood and water in thermal contact, you will again observe no heat transfer. So this is not the case. So we don't have to invent or use different temperature scales for different pair of objects. We can use one single universal temperature scale which can be used for every pair of every object or every material or system. Okay, so in this way we can define the temperature, which helps us to define the temperature from the zeroth law of thermodynamics. Okay, so the temperature can be defined in such a way that temperature of a system or an object is the physical quantity, that is, it can be measured, which determines whether the system or the object is in thermal equilibrium with another system or object in its contact or not. Okay, now what is the name? Why the name is the zeroth law? Okay, so zeroth law. Okay, now this whole endeavor of thermodynamics, that is, so before the zeroth law was stated, there was already the first law of thermodynamics. Okay, it was already been declared. Then it was realized that this whole endeavor of thermodynamics based on the ability to define a universal temperature scale. Okay, that we just stated, right? Because the zeroth law of thermodynamics helps us to define a universal temperature scale which is applicable or between all materials and object. Okay, so we can use a universal temperature scale which is valid for all materials and object. We don't have to use different temperature scale for different materials or objects. Okay, so now the thermodynamics and the first and the second law of thermodynamics are all based on the ability to define a universal temperature scale between all materials and objects. Okay, so and this we get from the zeroth, this concept of this universal temperature scale we get from the zeroth law of thermodynamics, the so-called zeroth law of thermodynamics, the statement of the which we stated that law. Okay, so in that sense we can say that now there has already been the first law of thermodynamics. Okay, so in that sense this law that we just stated is even more fundamental than the first law of thermodynamics. Okay, so this law is even more fundamental than the first law of thermodynamics. But the first law of thermodynamics was already been declared. Okay, so the name of the law was given, which is even more fundamental than the first law of thermodynamics. That's why it is called the zeroth law. Okay, so it is even more fundamental. So even less than the one. That's why the zeroth law of thermodynamics.